We have seen some properties of the most basic kind of periodic motion, namely simple harmonic motion, and I pointed out that simple harmonic motion is the very model or the prototype of all kinds of periodic motion, more complex periodic motion. Natural extension of oscillations or periodic motion is the idea of waves, both standing waves as well as travelling waves. So, we will now consider what we mean by wave motion and some of its fundamental properties. Imagine that you have a function f of x sketched in this particular fashion. So, it is some kind of disturbance, could be anything at all, and we will come across physical examples of it, as a function of some variable x, independent variable x, and it has a shape of this kind. So, this function here is f of x out here. It has got a peak and then it dies down on both sides, for instance. Now, what would happen if this disturbance changed its position with time? It moved, for instance, in the positive x direction with some assigned pre-assigned speed u, for instance. What would it look like? Well, at a later instant of time this thing would look like that, and then as time progresses it would look like this and so on, such that the peak goes on shifting. And the way to describe this travelling pulse, if you like, is to consider instead of this function f of x, to consider the function x minus ut, where u is got the physical dimensions of a speed and t is the time. Because for instance, suppose this peak occurred when f of x is some x bar. So, f of x has a peak at the point x bar. At a later instant of time the peak has shifted here, and it has shifted to a point given by x minus ut equal to x bar, because that is where the peak is when the argument of this function is at x bar, which would imply that the new peak, new peak is at x bar plus ut. In other words, the peak goes on shifting, and we would say that this pulse is moving forward with a constant speed given by this quantity u here. So, this functional form, once you specify this function f of x, this functional form replacing the argument by x minus ut would correspond to a travelling pulse moving in the positive x direction with a speed u. That is a fundamental observation, a fairly trivial one. What would happen if the pulse moved backwards? Well, you would then have to consider f of x plus ut, because now the new peak would not be at x bar plus ut but x bar minus ut on this side. So, that would correspond to something moving in the backward direction, in the direction of negative x. So, with this basic observation that a function of a combination of a space coordinate and time of this form describes for us a moving pulse in time, that basic observation helps us to understand what wave motion is all about in the general case. Now, of course, wave motion suggests that you have something that is periodic in space, and if it moves then it is periodic in time as well. And how do we describe that? Well, the most basic periodic functions are the cosines and sines. So, one could consider, instead of a general f of x, one could consider a cosine, which could also be a sine, or sine does not matter, or some combination of the form x minus ut. This would be a periodic function in x for a fixed t and a periodic function in t for a given value of x. On the other hand, the dimensions are all wrong here, because it is clear that x must have dimensions of length, for instance, and t has dimensions of time. So, we need to put in the argument of the cosine quantities which are physically have no physical dimensions at all, and that is done by saying, suppose I want the pattern to repeat in this fashion. I want this pattern to repeat after a distance lambda, for instance. Then the way to do it is to write this, exploit the fact that this cosine is periodic with period 2 pi, and write it in the form cos 2 pi x over lambda. That makes this quantity dimensionless. And similarly in time, if you want a periodicity capital T, make this minus on this side t over capital T. Now, that is a periodic function in space with period lambda or wavelength lambda, and this is called the wavelength, and this is the time period. It is periodic in time with a time period capital T here. Either a sine or a cosine of this gives me a periodic, basic periodic function of this kind. I could of course add to this whole thing, I could add some quantity here plus some phase delta, and that does not alter the periodicity properties of this function at all. It would be determined, this delta would be determined by saying what is this function or disturbance at some specific value of x and t. Once you fix that, this quantity delta gets fixed here. So the general form that we write down is some function of this kind and can be rewritten in many ways. For instance, you could write this also as equal to cosine of, if you call 2 pi over lambda a new quantity k, then this becomes x, minus 2 pi over capital T, you call it omega, then it becomes t here. So this quantity k is called the wave number, and it is 2 pi over lambda, and this quantity is the angular frequency, and it is equal to 2 pi over t, which is also equal to 2 pi times nu, where nu is the plane frequency. Very often in physics we call omega the frequency itself. It is actually strictly speaking the angular frequency, and nu is the frequency, the reciprocal of the time period capital T. But this distinction is, it should not cause any confusion, because by context we know what we mean. I will always use the symbol omega for the angular frequency and little nu for the frequency itself. Okay. So these are dimensionless quantities, and this is the basic model of a periodic or sinusoidal wave with wave number lambda k and angular frequency omega here. So once we have this in place, we can have waves of different frequencies superposed and so on and so forth. On the other hand, a wave which is travelling in the backward direction would correspond to a plus sign there. So cos kx plus or minus omega t refers to a travelling wave in the positive x direction for the minus sign, negative x direction for the plus sign. Whether we write this as kx minus omega t or omega t minus kx does not matter, as long as the cosine is there. For the sign, it just changes an overall sign. One could also put an amplitude for this wave, no reason why it should oscillate between +1 and -1 in magnitude in size. One put an a here, which would be the amplitude of this wave here. So this is the basic model or basic function which describes a moving wave, a moving disturbance, which is periodic in both space as well as time. Now a comparison of that with this thing here immediately tells us that the speed of this wave is easily determined. The speed of the wave corresponds to saying I take a particular part of this wave, say a crest, and ask what is the speed at which the crest moves, or a trough, and what is the speed at which it moves. This wave moves without changing its shape, and therefore whichever point I choose on this inside in a given wavelength, I ask what is the speed with which that point moves across on the x axis, and a simple comparison of that form with the general f of x minus ut shows that the speed of the wave corresponds to u equal to omega divided by k. All I have to do is to pull out a k, and then it is x plus omega over kt, and omega over k's coefficient of t gives me the speed of the wave here immediately. This thing here is called the wave velocity, or another name for it is the phase velocity. So it tells me the speed at which any given phase of the wave, such as a maximum or a minimum or any point in between, moves. So whatever a given phase does, the speed at which it moves is called the wave or phase velocity here. The reason for this distinction is that very soon we will come across another kind of velocity or speed associated with this sort of wave called the group velocity, and we will come to that in its turn. But here is a very simple idea that the phase or wave velocity is just the ratio of coefficients of the two of x and t respectively with the proper sign here. Alright, having said this, let us move on to some examples of such waves. The most standard example of all has to do with waves, transverse waves on a string. So, if I have a string and the string is stretched and then there is some tension on it and I let it move in this fashion, some disturbance moving on the string, the direction of propagation is this. The x axis say. On the other hand, the disturbance from the undisturbed string, which would be just a straight line, is in the transverse direction. So, this is a transverse disturbance or transverse wave of some kind, transverse displacement. And the question is, where does this come from? What kind of what's the way in which we can identify what's the speed of the wave, what kind of transverse displacements you can have, and how do I find the speed of this wave? Well, we have three properties associated with this wave, which is obvious from the way we have written it down. We have a time period t or a frequency nu, a wavelength lambda, and a speed u, and we need to know what is the connection between these three quantities, and that is very straightforwardly done. The way we wrote it down, remember that we said u was equal to omega divided by k, which is equal to 2 pi nu divided by 2 pi over lambda equal to nu lambda. So, the relation between the speed of a wave, the wavelength of the wave, and the frequency nu is simply that the product of the frequency times the wavelength is equal to the speed here. That is a basic fundamental relationship which we learned in elementary physics. Here. Now, how do we determine the speed? That is a property which depends on the kind of wave you have and the medium in which it propagates, medium if any in which it propagates. For instance, in the case of the string, we could derive what the speed is by dimensional arguments. If this string has a tension T here, then it is clear that what the speed can depend on is a material property of the string which is under this tension. So, it must depend on the tension T. I am sorry for using the same symbol for the tension and the time period t, but this is standard notation, and I am not going to bring in the time period anymore. I am going to always talk in terms of the frequency or the angular frequency. So, capital T will stand for tension from now on. So, this frequency or the speed u must be a function of this tension. It should be a function of the mass of the string. In fact, it is a property which is of the string as a whole. So, it is not the entire mass that matters, and as we will see in a minute, but the mass per unit length. So, let us suppose the string has a mass m and the length of the string is L, and this is the length of the string. Then simple dimensional arguments to find a quantity of dimensions speed is very trivial, because this quantity T, physical dimensions of the tension. So, let me write it down in this form. This tension is a force which is ml t to the minus 2, and then the mass m has dimensions m. So, it is clear that to find a velocity you need to divide this out. Tension over mass will kill this, but you got an L here. On the other hand, if you divide by the length as well, this is equal to L. So, if you form the combination T divided by m over L, then that quantity has dimensions L squared t to the minus 2. So, the square root of this has dimensions u. So, this must be u times some constant. So it immediately tells us that the speed of waves on the string is equal to the square root of the tension of the string divided by the mass per unit length, or the linear density, mass density of the string, multiplied possibly by a constant, which will turn out to be unity. We will derive this exact expression a little later, and it turns out that in this case this formula is exact, and this turns out to be T over rho, and this rho is the mass per unit length. The string. So that tells us that this is a material property. It is a property now of the property of the string itself, namely how much tension it is subject to and what the mass per unit length of the string is. Okay. In the case of an actual metal string in which waves, transverse waves propagate, depending on the kind of waves you have, some elastic modulus of the string is, or of the material of the string, is what is going to play the role of this tension there, something related to it. What about a thing like sound? What about sound waves? Well, there we have a formula which is actually quite easy to derive. As you know, sound waves are created in air, for instance, or in a gas, are created by changes in the local density. So compressions and rarefactions of this gas in a periodic fashion lead to sound, or propagate in the form of sound. Now what can the speed of sound in a medium be dependent on? This u must depend on an elastic property of the medium, namely air in this case, and in this case, because it is a pressure wave, it must depend on the bulk modulus. So this again must be equal to the square root, apart from a constant, of the bulk modulus K which has dimensions of stress or force per unit area, if you recall, divided by the density of the string of the gas, the mass density. And let us see if this is true or not. The way to do this is to write the formula down for this times a constant, and once again it is possible to show that this constant is 1. This is what dimensionality dimensions give you, dimensional analysis gives you, and once I have a formula for the bulk modulus of a gas, we are done. This is the speed of sound in this gas. Now what is this bulk modulus equal to? If you have a change in pressure delta P, and that corresponds to a change in volume delta V, an increase in pressure will decrease the volume, so delta V is negative minus delta V, divided by V is the strain. So this is the bulk modulus, this is equal to K, the bulk modulus. And we need to compute this. Now you have to tell me whether the process through which this gas gets this changes in pressure, the rarefactions and compressions, is adiabatic or isothermal. Well, in the simplest approximation, if it is isothermal, then we know that PV is a constant for an ideal gas. So it says PV equal to constant at a given temperature, fixed T. This would imply, of course, that P delta V plus V equal to 0, or P equal to minus delta P over delta V over V, which means that the isothermal bulk modulus, which I should really call K subscript T to show that it is isothermal, is equal to the pressure itself. So it says this is equal to the square root of the pressure divided by rho. Since K isothermal equal to the pressure for an ideal gas. This was Newton's formula. Newton derived this formula for the first time, and he said that the speed of sound, u sound in a gas, is simply given by the square root of the pressure of the gas divided by rho. However, it was soon seen that this is not quite correct. Experiment did not match this. Once the speed of sound started getting measured with some accuracy, there is a small change in this formula which is quite measurable, and the matter was fixed by Laplace, who pointed out that the changes, the rarefactions and compressions are happening so rapidly that the process is essentially adiabatic and not isothermal. Once that happens, then what we must put here is not the isothermal bulk modulus, which is the pressure itself, but the adiabatic bulk modulus. And the adiabatic process has, if you recall, PV to the gamma is constant. This is what an adiabat does. For an adiabatic process. This will immediately imply that P gamma V to the gamma minus 1 delta V plus delta P times V to the gamma equal to 0, and now it is clear that this will imply that K adiabatic is equal to gamma P and not P. Okay. And therefore, if you put that in, the correct formula for the speed of sound in a gas should be the adiabatic bulk modulus, and that is given by gamma P over rho. So, this is the formula, correct formula for the speed of sound in a gas, and this is due to Laplace, Newton and Laplace as modified by Laplace. Notice that for an ideal gas, which is the case we have considered here, the speed of sound is actually dependent only on the temperature of the gas, and that is easy to see, because if I write U sound squared to get rid of the square root sign, it is gamma P over rho, the density. This is equal to gamma P V, you can multiply by V, by rho times V, multiplying both sides by V. But then PV for an ideal gas of n particles is gamma times n times K Boltzmann times T. That is the ideal gas equation of state. PV is n gamma K Boltzmann T, and we are going to study this when we study heat in a short while, divided by the density of the gas, the mass density multiplied by the volume, which is the total mass of the gas, which is equal to the number of particles in the gas multiplied by the mass of each molecule of the gas. This is mass of a molecule. And therefore, this thing here becomes equal to gamma K Boltzmann T divided by m, which is a function of T alone. So, we have this interesting feature, important feature, that the speed of sound in a gas is essentially a function only of its temperature, as long as you can make the approximation that the gas is an ideal gas. Does not depend on any of the other thermodynamic variables. And one can further interpret this in the following way. After all, we know today that heat is a form of random molecular motion. In fact, what we call heat is essentially in these systems the kinetic, average kinetic energy of the molecules due to the random motion that they undergo. So, this K Boltzmann T can be rewritten in the following way. We know that mv squared average, the average kinetic energy 1/2 mv squared of a gas, we know that this quantity is equal to 3/2 K Boltzmann T. This is called the equipartition theorem, and I will come back and see how we can establish this in a fairly simple way. So, if you put this in out here, then K Boltzmann T can be removed in favor of mv squared, the m cancels out, and this becomes also equal to gamma over m, 2 cancels out here, and K Boltzmann T is m v squared divided by 3, which is equal to gamma times v squared divided by 3. So, we have a way of relating the speed of sound in a gas, ideal gas, to the ratio of the specific heat Cp over Cv times the mean square velocity or mean square speed of the gas, mean square velocity in this gas. So, it is related to a fundamental quantity, namely a microscopic quantity in this case, and it is of the order of this quantity here, because these quantities are of order unity. So, it actually is making a very direct contact with what is happening in the system at a molecular level, the speed of sound, from this very simple argument here. Okay. We will come back to waves in 3 dimensions, what these waves are like and so on as we go along. Okay. Now, let us go back a little bit to waves on a string. We have already seen that the speed of the waves on a string is controlled essentially by the material properties, the square root of the tension divided by the mass per unit length. What controls the frequency? Well, I can take this string and swing it at whatever frequency I like. So, in that case the speed is fixed, the frequency nu are determined by me, determined by us. For a free string, if I swing it up and down at some given frequency, the speed of the waves on it, the pulses on it, is determined by the tension and the mass per unit length. The frequency is determined by me. Therefore, this implies that the wavelength is determined. On the other hand, suppose I take this string and clamp it at both ends here, and then I pluck this and set up waves in it. So, you could perhaps have a wave which looks like this, and as a function of time this goes up and down this time. One of the possible modes on this string is of this form. And now, it is the wavelength that gets determined, because you must have nodes at these 2 points. So, the boundary conditions fix the wavelength or restrict it to a set of wavelengths, possible wavelengths. All those wavelengths are allowed which have nodes at the 2 end points, and then the frequency gets determined because u is given by the tension and the mass per unit length. So, when we talk about free wave propagation in a medium, in general it is the frequency of the source that determines the frequency, and when light passes through a prism, for instance, it is the frequency of the source that determines the frequency of vibrations, and the wavelength gets determined depending on what the speed in the medium is. On the other hand, when you have a confined medium of this kind and you set up standing waves in it, then the wavelength gets determined by the boundary conditions, and it is the frequency that is determined by the connection, which essentially says that u equal to nu times lambda. We will look at examples of both these things here. So, the next step is to see what are the possible wavelengths that are allowed in this case here, and let us do that next.